Well, hello everyone, and welcome back to Adrian's Digital Basement. On the last video, I was trying to work on and repair an IBM PC XT clone motherboard that I have that has been misbehaving. I was pretty sure I figured out what was wrong with the motherboard in the last series, and spoiler, if you haven't watched it yet, I recommend you watch it first, because what I did is swapped out a few chips after checking with the oscilloscope and reading through data sheets to try to figure out what was wrong, and I couldn't get the board working. The board has a problem where if any interrupts are fired and the interrupts are enabled, meaning IRQ 0 through 7 are turned on, then the handler that should be running isn't working, or something weird is going on where the computer basically freezes or gets stuck in a loop where it stops executing code. So depending on the ROM you're using, the BIOS ROM or diagnostic ROM, when it goes to check one of the interrupts, it just sort of hangs. And we see different things on the oscilloscope depending on which BIOS we're running, but either way, it seems like anytime the interrupts get triggered, or at least interrupt 0, which is the time of day, just the regular interval timer that's happening all the time on all PCs, the system freezes. So I wasn't really able to figure out what was going on, and that's what I want to try to remedy in this video. And I've put some thought into some stuff to try, and it involves the logic analyzer and another motherboard and doing some comparisons and stuff like that. So without further ado, let's get right to it. In the last video where we left off, I was really struggling to understand the timing of the entire interrupt sequence, let's call it. So here's the CPU. This is the bus controller 8288. This is the PIC, or programmable interrupt controller, and this is the PIT, the programmable interrupt timer. So the PIT is set up to generate and fire off a signal every 18 milliseconds or so, which goes into the IRQ 0 line of the interrupt controller. Then this subsequently fires off a signal to the CPU to say, hey, there's an interrupt that's happening right now. And in coordination with this 8288, this sends a signal back to the PIC here to say, okay, interrupt is acknowledged. And there are two pulses that come from this chip that go back into here. And that's what I was measuring on the oscilloscope. And that instructs the interrupt controller, the PIC, to write to the data bus the actual value of the interrupt, which the CPU is supposed to then read and then act on. It's an interrupt vector, which tells this where it needs to go in memory or in ROM or wherever in the memory space so it can handle the interrupt. This is where I think the problem is happening on this board. There's something going on here that's preventing the CPU from being able to read the interrupt vector properly. I swapped out the CPU with a different one. We swapped out a different 8288 and a different interrupt controller. That's this chip right here. And that doesn't seem to make any difference whatsoever. So I created myself a little list of things which I think are potentially issues that I need to look into. And we have no particular order for these. Now, I'm thinking that there's probably a bus conflict that's happening with this system during that phase where the interrupt controller is writing the vector to the data bus. And that's where the CPU is supposed to pick it up. We're seeing some strange signals on the oscilloscope during that phase, but what's not clear when I went to the data sheets for the interrupt controller is where in the cycle of those int-A signals, those are the signals coming from the 8288, where is it actually picking up the vector from the data bus? The timing diagrams are extremely vague, so I'm thinking there's a bus conflict in there, but I don't really understand the timing. So some stuff that I want to work on in this video is I want to get another motherboard, a working XT motherboard, and load the same BIOS codes into it. And then I can scope the signals. We can look at the same exact signals we're looking at in the last video on the working board, and we can see what it's supposed to look like. Because there was some weird stuff that I was seeing on this board where when I think the PIC, the programmable interrupt controller, is driving the bus for the CPU to pick it up, we're seeing some like weird floating values or things that are like in the middle, which kind of seem like a bus conflict. Now what I have is a 32-channel logic analyzer, and that can really help us understand the entire sequence of what's going on all the data bus lines simultaneously. The problem is logic analyzers are not good at detecting bus conflicts because they're threshold devices. They are high or low, and it doesn't have a way to register values that are somewhere in the middle from a bus conflict. Now, if a bus conflict is actually happening during that phase when the CPU is going to be trying to read the vector, you're going to get weird random values. And that's where trying to use known good hardware is a good way, just so we can kind of see how it should look, at least on the oscilloscope. And that would be before we jump to the logic analyzer. Now, here's something to consider. I talked about this in the first video, that the ROMs And all of these peripheral ICs, so these two ICs and these two ICs, they all exist on a data bus called the XD bus. This data bus is different than what's on the ISA slots. That's just the data bus, the D bus, except for slot 8 on the original IBM PC XT. That is actually on the XD bus, along with the peripheral chips and the ROMs. But I think on this motherboard, all the ISA slots, including what the CGA card is on, is just on the normal data bus. The CPU itself has multiplexed address data bus, and there's some bus transceivers that hang off of it and latches and stuff that generate the regular data bus, the D bus, the XD bus that this stuff is on, and then the MD bus, which is the memory data bus. That's what the RAM is on. So they're separated from each other. And that means that from a bus conflict standpoint, because I've been measuring everything off of these ROM sockets, the bus conflict has to be coming from something on the XD bus itself. It won't be on the CPU or on the RAM because those are completely separated through bus transceivers. So one thing I wanted to try is I wanted to look at the data bus lines that I'm seeing this bus conflict on, and I want to look then at the data bus lines that are on the CPU itself just to kind of see what is the CPU seeing during that same phase that we're seeing what looks like a bus conflict. Okay, once I show you what I'm seeing, it'll be a bit more clear. All right, so I'm going to be using the oscilloscope to take a look at the data bus lines on one of the ROM sockets because this is the XD bus that's shared with everything. And we're going to start with pin 11, which is data bus line 0 or XD0. And on the oscilloscope, the yellow trace is the int A signal. This is the interrupt acknowledge signal that comes from the 8288 that goes back to the programmable interrupt controller. And it is during this second pulse where the interrupt controller is going to be driving the data bus to put that interrupt vector onto it for the CPU to pick up. So we'll start on pin 11, which is data bus line 0. And I reset the system. And there is that floating value. And I was seeing that exact thing in the last video. So data bus 0 is weird. It's floating. I don't know why, but it is. We go to the next data bus line. So we're on data bus 1. This line is kind of down around ground, and then it sort of floats halfway through. Don't know if that's on purpose or a problem or what the deal is, because I don't know how that's supposed to look. Now we're on data bus line 2, which is pin 13. Same thing, kind of like that half floating thing. Now moving over to pin 15 is data bus line 3. That's just high, which actually I think is what it should be. And then we have data line 4, that floats. That's not right. And then we have data line 5, we're getting like that partial float. Data line 6, partial float. And data line 7, it just stays low. Now, based on the timing diagrams that I've seen, the important part of time is right here in this chunk of when this signal is low, int A is low. And we looked at these timing diagrams and they're kind of vague, but ultimately what I'm thinking is happening is that when this goes low, that's int A, in that section, this is where the bus is getting driven by the interrupt controller. Well, it shows it being driven at that first pulse, but it's not. Well, I mean, the data bus might have activity on it, but certainly not coming from the interrupt controller. The interrupt controller does only drive it here in this second pulse. And this diagram is for the 8088 and the 8085, and that's why the 8085 shows 3 pulses, and yeah, anyways, kind of annoying. If we look at the same timing diagram for the data sheet for the Intel version of the chip versus, I think, the Mitsubishi version of the chip, it's very similar. It kind of shows that the data bus is being driven in this section right here, and it does say down here, cycle 1 in 8086 and 8088 systems, the data bus is not active. So this is cycle 1, that is cycle 2. Cycle 3 does not apply at all on the 8088, it's just not used. So essentially, right there where I'm circling the mouse, that's theoretically where the bus is being driven. And it kind of shows it starting after this signal goes low, and it ends somewhere after the signal goes high, according to this diagram. Now, what we didn't take a look at in the last video was the data sheet for the 8086 or 8088. I think the timing is going to be essentially the same between the two of these parts. And here it is. This is the interrupt acknowledge sequence. So there's that int A, first pulse, nothing happens. Data bus should be floating or whatever. It doesn't really matter what it's set to. But on the second pulse, that's the vector right there. And it kind of matches up with what we saw on the other data sheet where after a little while, it starts getting driven and it should be driven even after it goes high. And when we look at a diagram like this and it shows that the type vector is actually overlapping with that int A going high, it kind of implies that the CPU is probably grabbing it like somewhere in this section right here. And when we look at this particular waveform, I forgot which data line we were on there, that looks completely valid. This should pick it up as a 0 from as far as the CPU is concerned. But going back to data bit 0, I mean, that's That's a weird floating value. So that one doesn't make sense. So that it should be a 0 because it's interrupt 0 that's triggering it. But what about this one? It changes midway through. So what does this even mean? This has got to be some kind of a data bus conflict that's happening, because there's just no way, well, I just really don't think at least, it should be doing this during that phase of the int A pulse. That seems like a problem. Now, when just sort of thinking about what might be going wrong with this thing, one thing I thought about is, obviously I'm using a ROM emulator here and not a physical ROM. And I'm loading firmware onto this, and I haven't had any issues using this ROM emulator on this motherboard before. Now, what if something is just acting up on the one ROM? I don't know. I don't want to blame it, but it's certainly something that I should think about at least. All the ROMs that I run on here seem to work still. Like I can run XT-RAM test and it's working perfectly, and that runs out of ROM entirely. But something obviously is causing a bus conflict, or I think something is causing a bus conflict. I can't say obviously, but it seems like that's happening. So I think what I might want to do is, while we have that pulse happening for the int A signal, the yellow trace, I want to look at the chip enable lines on the one ROM and just make sure that it's not being enabled. I mean, I can't necessarily blame this, but what if the chip select logic on this board, whatever it is faultily generating a chip select for this? Let's investigate that. So I'm on pin 22, and I think that's the chip enable line. And I'm not really seeing any triggers happening, but the computer's almost certainly just crashed or whatever right now. So here, I'm going to reset the system. All right. So what that's telling me is, while the trigger was happening for int A, this chip was not being turned on. At least not on that pin, not pin 22. Now we have a couple chip enable lines. I think pin 20 is also a chip enable line. You can use either one of those. So let's use that one. And let's just run this in auto mode. Nope, it's not being triggered right now. And we'll turn on the system. It's definitely toggling the chip enable line. You can kind of see it up here, but it is not being turned on during that time. So that's a good thing right there. So it's not being turned on. So if we saw it turned on maybe halfway through this pulse, we saw that float happening where the data line kind of went up to here, like there was a bus conflict and it went up there. Either way, that doesn't rule out the one ROM entirely. And I'm wondering if I should maybe switch this out with just a normal EEPROM just to kind of rule it out. But actually, you know what? Before I do that, why don't we take a look at the data bus lines on the CPU when I do this reset process. So first I'm going to pick one of the data lines that looks suspicious. So I'll reset the system. Okay, well, let's pick, I'm going to pick data line 2, because this is the one that sort of has that weird float halfway through. And if we go to the schematics for the IBM, we can look at the math coprocessor, and we were looking at data line 2, which is pin 14 on the math coprocessor. All right, I'm on pin 14. So keep an eye on that red trace, because that's what's going to change. Okay, so I'm on pin 14 on the math coprocessor socket, and it has that weird wavy bit there. And this is the section where I think the CPU is trying to read the data bus. That kind of coincides, let's go back to the ROM socket, with that weird sort of semi-floating thing. I'm going to go to data line 0. Let's look at how that looks. Okay, so this is on the ROM socket, data line 0. It goes from high down to that sort of floaty thing. And let's check it on the CPU now. I'm on pin 16, which should be address data line 0. I'm going to reset the computer. And it's just high. Okay, and let's look at address data line 1. That has that weird wavery thing. The next one has it as well. And now I'm on address data line 3, so pin 13. It's just high. And if I go to data line 3 on the ROM socket, it's just high. Data line 4 on the ROM socket, that's another one of those floating ones. And that's pin 12 on the CPU socket. Let's see how that comes out. Is it going to have that weird wavy thing, or is it going to be high? It just comes up as high. So it appears to me that when the PIC is driving the data bus, and it looks like this, on the CPU side, that's going through a buffer, it ends up looking high. But when we look at data line 1, and it has this sort of halfway thing, and now I'm on pin 15, which I think is address data line 1 on the CPU, we get this weird wavy thing happening. And that's just strange. Let's zoom out a little bit and see if we have any more of that waviness happening anywhere else. No, not really. We seem to have this little bit of a, going up thing here happening, but it's certainly not wavy that way. Let's zoom in on that and see if we can see a little bit more to it. I'm not 100% sure what this waviness means, but it's just interesting that it kind of coincides with that strange stuff we're seeing on the XD bus coming from the PIC, the programmable interrupt controller. Now, I suppose for completeness, one thing we can do as well is look at the data bus that is coming from the RAM. So this is the memory data bus lines. I'm not sure that the RAM chips are necessarily going to be driven at the same time when the PIC is driving the data bus, the XD bus. I don't know if it's actually all going to be connected together. It just depends how the logic works. I think this is data bus 0, or data bit 0, I mean, and that's low. And then that one, which is the parity chip on here? Oh, it's labeled on the board. Okay, so this is 0 right here, again, so it's just low. And compared to what's on the ROM socket, if I reset the machine, well, that's that weird sort of halfway thing. Now, if we look at 1 on the RAM chip, data bit 1, it's transitioning partway through. Okay, and when we look at 1 on the ROM socket, I mean, that kind of matches, doesn't it? Going back to the RAM chip. So here's 1 on the RAM chip. Yeah, very interesting. So there's back on the ROM socket. Ah, okay. Is this coming from the RAM somehow? So now we're on data bit 2, and this is on the ROM socket, so the XD bus. And now let's go to the RAM chip and see if it looks the same. Oh, that's just driving it high. So it doesn't look the same at all. Okay, this is 5 on the RAM, which has that partial thing where it kind of goes up. 3, 4, 5 on the ROM socket. And it's floating. All right, well, this is curious to me. So it feels like this bus conflict we're seeing is with the RAM. And it feels like when the RAM or something on the RAM side is driving this signal high and the programmable interrupt controller is trying to drive it low, they fight with each other and you get this half value. Now, one thing that kind of sucks is I don't have schematics for this motherboard. All we can rely on are the XT schematics from the actual IBM motherboard, which is not going to match exactly the same. Now, on the actual IBM motherboard, it's the LS245 that connects the RAM, the MD lines, these are the data bit lines, data bus lines, to the CPU's data bus lines. Now, on this motherboard, I'm not 100% sure where that might be. It could be this chip right here, because that's in a socket already. And I don't think I put that in a socket, because my sockets are usually the round hole type, and this is a non-round hole type socket. So let me pull this one out. And one way I can test to see if the RAM is now broken is all I need to do is just simply set this up to run the XT RAM test, and we will see very quickly if there's no RAM found on the motherboard anymore. And that's what would happen if this were the bus transceiver for the RAM. Okay, turning on the system now, it does not even post at all. So that LS245 is obviously used for something else. Yeah, because it should be running, well, I can just put this back in and we can see what this does, but I'm pretty sure it should be running the XT RAM test now. Yeah, that is. Okay. So that is not for disabling the RAM. The RAM on this motherboard is connected through a different bus transceiver. Now, there are some extra bus transceivers over here, and I can try pulling these out, and we can just see what happens. Let's take this one out first. This one here is a latch, but this one's an LS245. So we turn on the system now. Okay, well, yep, okay, all the RAM is bad. So that is the one for the RAM. There's no more RAM left on this machine. There's 0 RAM. So if I pull the jumpers off of here and we're back to just running GlaBIOS, let me turn it on. It no longer does anything. It is completely unhappy. There isn't even a post beep or anything like that, but let's just check to see what it looks like on the oscilloscope now. So when I turn on the system, no interrupt ever fires. So it needs the RAM for anything to even happen at all. Now, I did just switch it over to run the SuperSoft BIOS. I'm curious if this, oh, look, it still posts. So even without RAM, it still is doing something. It's gonna fail though before it even gets, yeah, it's unhappy about the 16K of RAM not working. I think RAM is required for any interrupt vectors to actually work. I mean, it's trying to do all the RAM testing here, but it skipped over everything else after the critical area. It's now running the RAM tests, which are normally down at the bottom of the screen there. I think all of those other tests that this thing can do require some amount of memory. I just wanted to see if removing this chip, the connection to the RAM, removed our bus conflict. Because somehow it seems that there's a bus conflict between the RAM and the XD bus that doesn't prevent the system from running, but then, well, we see the effect of it. You know, just for poops and giggles, I'm going to swap this chip out. And it's really just because I happen to have one sitting right here. I don't think it's necessarily going to fix our problem, but, you know, you never know. Who knows? Okay, here we go. Turn this on. Yep. You know, it's so funny. If anything, doesn't the little shelf here look a little sooner than the other chip? I mean, I didn't put in a faster chip. It's just another LS chip. But doesn't this seem like it's happening a little bit more quickly than it was before? So I am on, what line am I on? I am on data bit 2. Let's try the other ones. I'm on data bit 1 now. And then data bit 0, I think, should be floating the whole way across. Yeah, same thing. Let's use one of the cursors to see if this really does move. So I feel it's like happening right there. Power this off and we'll switch back to the original LS245. All right, so data bit 0, that one's floating all the time. But if we go to data bit 1, yeah, it's moved. It absolutely moved. So that confirms, let's try data bit 2, by the way, that confirms, yeah, same. That confirms we're having a conflict with the memory data bus, the RAM data bus. But why? But why? So the chip I removed from this board, it was U13. So it doesn't match the U9 marking that's on here, but at least the pinout's going to be the same. I'm assuming the pinout's going to be the same. So we can look to see at the enable signal, that's 19, and the direction signal. Well, let's take a look at those. I am on pin 19. This is the enable signal. I don't think this chip should be enabled at all while the PIC is writing to the bus. When it's low, it's enabled. So it is definitely enabled. So it kind of makes sense to me that if this chip is the source of our bus conflict, and currently the whole time it's enabled, is this chip theoretically is only connecting the MD bus that goes to the RAM over to the data bus, which is the isolated bus that goes over the CPU, not the XD bus. But what if this motherboard doesn't have an XD bus? And let's do some measurements with these to see. We still have continuity that we can measure. Let's see if there is actually separation between the ROM data bus and the RAM, because maybe on this board, they're not separated. I didn't even consider that. So we'll just go to data bus 0 line, and this is what it sounds like if we have continuity, and here, no continuity. Okay, so it is separated. And this is data line 1, and there is nothing on the RAM. If I go to data line 0 on the ROM, it should not be on this LS245 that I just took out, because this is only separating, theoretically, the memory from the CPU, and the XD bus is separate. So, well, first let me validate for sure if this is handling the RAM. Yes, there it is right there. And each of the data bus or bits should be on this chip. They are on the right side, or the side closest to the back of the bench here. Now I'm on data bit 0 on the ROM socket, and let's see if it's on the other side here. Nope, it is not. So that means that this conflict that we're seeing on this bus is not coming from that chip specifically. It's the RAM going to that chip through to the regular data bus, and then there's another chip that connects that data bus to the X bus. And I just have to kind of probe around here and look for other LS245s to find out where that is happening. It's this one that's soldered onto the board. That's the one that's probably creating this XD bus. So I bet you, if I look at the other side of this, one side of this should be XD, which is the ROM and these peripheral chips. The other side should be the D, just the data bus. That's probably going to be found on this chip. Yep, there it is right there. And yes, one side of this goes to the RAM. The other side of this chip goes to right there. And then this pin, which is the A and the B side, goes to the ROM sockets. Well, one thing I've just noticed, by the way, data bit 0 on the ROM socket, it goes to that chip from there, and then to here, and that connects to this chip. And then what should be data bit 0 on the RAM, which would be the bottom pin right here, because this matches up to data bit 0 on the ROM sockets, it's this RAM chip over here. That's data bit 0. The motherboard has a 7 written right there. It's hard to see, but there's a P and then 0 through 7. Well, that's wrong, because this is obviously data bit 0. And again, the reason why I know that is because on the LS245, on one side, it connects through to this other side, which happens to match up to this chip right there. So that's probably going to the CPU or actually an LS245 over there. And then this side, which is the opposite side of that exact bit matches, this is going to the ROM sockets. I'm sorry if that's a little bit hard to follow, but I guess what I'm trying to say is that data line 0 on the RAM, which is this pin 11, that converts over to this A8 pin on this side, which is pin 9, and that goes to data bit 0 on the motherboard to any other chips that are on that data bus. And I happen to know that, for instance, those lines are available on the ISA slots. So there's that D0. And then that D0 line that I've been tracing makes its way to this LS245. This is on the real IBM, of course, and that makes its way to the XD bus. And it's the XD bus that we know is going to, for instance, the ROMs, and is going to all the other peripheral chips. So it does seem that the design of this board does coincide with the way the actual IBM is. And hilariously, it looks like there's a flaw in the schematics because there's the enable pin for the LS245 that creates the XD bus. That signal comes out of pin 19. It makes its way up here and it goes into that chip, but those are inputs as well. So this doesn't actually show that, well, there's anything driving that pin. My assumption is it's probably just connected to ground. So I'm just gonna check that on this motherboard. So we're looking for pin 19. Actually, no, it is not connected to ground. So that's kind of odd. So something is driving that particular signal. It's just not indicated on this schematic. Anytime you have a joint, by the way, between two wires, you have a black dot. That's the way IBM did it. But that G signal, just an island. And what would change would be the direction signal, which happens to be pin 1 on it. So if we look at pin 1, you know, we do have pulses there that change the direction. And what the direction does, if we go back to the schematic, that changes the way this is connected. So one direction would be whatever's on the A side gets copied to the B side, and you flip the direction, and it's vice versa. Now, if you disable the chip, so the chip enable is active low. So if that goes high, then what would happen is this chip won't do anything. It won't copy anything to anywhere. But it appears, because it is enabled, as long as the direction pin is set appropriately, then whatever is found on one side is going to be copied over to the other side. And the reality is, because the interrupt controller is trying to write to the data bus for the CPU, what's on the XD side here needs to be copied over to the D side, which means it doesn't make sense when we're taking a look at the ROM sockets, which, remember, is on the XD side here, that we're seeing that weird bus conflict that seems to be coming from the RAM. That doesn't make sense. And that's because this chip should only be copying what's on the XD side over to the D4 side, not the other way around. So why are we seeing a bus conflict the other way? It's like this chip is bad or broken, maybe. The next logical step I would do is look at the data sheet for the LS245 and figure out which direction is which. I can never remember off the top of my head when the direction signal is high or low, if the A goes to B or the B goes to A. I need to try to figure out the bus conflict. But I think before doing that, I think it's time to just bust out another motherboard. This is essentially almost the same motherboard we're working on here. It's slightly different, just looking at the board, but the differences are extremely minor. So I think this is a perfect test case, A, to make sure that this motherboard, A, works, and then B, transfer the one ROM over to it and make sure all the ROMs that I have in there actually do function properly in this. And then we can start poking around and looking at those signals just to kind of see the difference with the programmable interrupt controller on this board versus this one that's not working. So on this board, every single IC is in a socket, which is kind of cool for troubleshooting, actually. Problem is, I can't add this right angle adapter for my ISA slots because the 16-bit part hangs down and it touches the chips that are in socket. So I have to put the CGA card directly into the motherboard. But even with that said, there's just some kind of random XT BIOS on this board, and let's see if this thing actually works. No. There's nothing to believe that there's anything wrong with this board, so maybe I just need to give the chips a push. A couple of them didn't really feel like they were in all the way. What if there's a problem? A problem that's, I mean, what could the problem be? The power supply or the video card? I don't think it's the video card because I was testing originally with my IBM CGA card. What's happening here? Okay, hold on a second, everyone. Oh, let me take the BIOS out of here and let's put the one ROM from the other one in, since I have a bunch of different diagnostics I could run based on the stuff that's on this one ROM here. All right, the one ROM is in, no jumpers are installed. That means GlaBIOS should be running. I do have a speaker hooked up, so we should hear a beep. Wait, what's happening here? What is happening? I don't understand what's happening. How could this not be working as well in exactly the same way? Let's put on the jumpers and see if, well, let's start with the RAM diagnostic. So that's this configuration right here. Okay, so this motherboard is behaving exactly like the other one. Wow, wait a second, what? How could both these boards be behaving in exactly the same way so far? I don't know for sure, so I'm gonna put the jumper on so we can run super soft. Let's see for sure if this is identical. If this freezes on interrupt 0, I don't know what to think. I do not know. No, this can't be, right? This can't be. Okay, here we go. Hot interrupt. No. So, okay, so this one is not working for another reason. Okay, yeah. There's no keyboard plugged in, so it's unhappy about that. Let's get the speaker unplugged. Okay, so this does not have exactly the same fault as the other one, but it kind of begs the question, what's going on with the XT non-turbo BIOS? It's quite possible that the GlaBIOS that I have on here, I've modified in a way that doesn't actually work. And well, I don't know why this board didn't work with that existing BIOS. So what I'm gonna do is we're gonna switch to the AMI BIOS and let's see if that works. Because that one was not working. Oh, wait a second, everyone. Oh, hold on. You know why it wasn't working? Because I had the switches wrong. Yeah, we're really doing an amateur hour on Adrian's Digital Basement here. Let's use this to help me figure out exactly how it should be set. Yeah, I should have realized that this was the problem. Okay, so I had these switches just set to a random configuration, probably for a VGA card. And I bet you that's what was going on. Yeah, this is not configured appropriately here. And the hint was the AMI BIOS just gave us a flashing cursor, which kind of told me that probably something was wrong. Okay, here we go with AMI BIOS. Yes, it is working. Oh, and it's counting the RAM. Okay, well, that's what it should do. So there's nothing wrong with this board. Okay, I was thinking I was losing it here. Hey, this XT AMI BIOS actually ticks the speaker as it counts up. Yep, keyboard error, of course, because not plugged in. Let's remove the jumper so we go back to GlaBIOS and let's see if it does work or doesn't work. It does work. And I have it set to super fast, which means, it doesn't really count up the RAM. It should be going to basic here, but, oh yeah, there we go. Cassette basic by Sun Up Computer. Talk about ripping off IBM's code. That's funny. They've modified that. Well, I have to tell you, I am very relieved because I really was thinking that something else was going on that was causing this board not to work exactly like the other one. And I honestly, I wouldn't know where to go from there. Anyhow, back to the original plan. Just one more time, I'll make sure this works. This is with the other CGA card in there. Good, it works. This confirmed a few things for me. It tells me that the one ROM itself is fine. It's not damaged. I could obviously swap the parts from the other board onto here and see if they work or not, but I'm pretty confident to say that those do work. So this scope probe, which will be the yellow trace that's hooked up to the int A signal that comes from the 8288. And we're going to do exactly the same thing where I'm going to probe on the data lines on the EEPROM socket, and let's just see what we see here. Okay, well, right off the bat, obviously this is what a normal working system looks like. We have interrupts triggering constantly, and this is because, of course, that timer is running non-stop once the system is booted. And obviously the thing is waiting for me to like push a key or try to boot, or actually we're probably in basic, to be honest, right now. So that's data line 0, data bit 1 certainly looks fine. Data bit 2 looks perfect. I mean, we don't see anything that looks like a bus conflict at all happening. There's data bit 3, data bit 4, 5, 6, and 7. So everything looks perfect. And exactly how I would expect it to look, to be honest. Part of the problem is I would like to replicate the position the other one was in where it would get stuck after that very first interrupt. In fact, you know what? We can replicate it, I think. Let's see. Let's figure out the triggering here. Triggering is on the falling direction. Remember, we want to trigger on this signal going down. So if I put this into single shot mode, I think theoretically that should show us the very first time we get that pulse. There it is. Okay. So from my understanding, according to the timing diagrams we looked at, what we see right there, this should be the bus, the XD bus in high impedance mode, which is probably why it's drifting up that way. And then what we're looking at there is data line 7. Now, for the very first interrupt vector that happens on interrupt 0, now when it comes to what we should be seeing on the data bus for the very first interrupt 0, like when the BIOS is first posting, after talking to Greg about that, what we should see on the bus is hexadecimal 8. So when the programmable interrupt controller sets up the data bus, it should be 0001000. And of course, this is data bit 0 starting on the right side, at least a data bit, and that is 7 over on the right side. So what I just looked at, we just captured on the bus there, or on the oscilloscope, this was data bit 7. So let's go through and look at every single data bit, and let's see if it just matches up to exactly what we expect. So each time I do this, I'm going to have to hit single shot while the computer's off, turn the computer on, and we just wait till it captures. There it is. So from what I get from the timing diagrams, when we look between these two cursors, this is what the programmable interrupt controller is driving the bus at that exact moment. When int A goes low, in this section, this is the relevant thing we're seeing. And we need to make sure there's nothing floating, nothing weird looking in there. That looks correct for a 0, and that's data bit 0. Okay, perfect. Okay, so data bit 1 is a 0. This is going to be a long and tedious process, but it looks like this motherboard does not have the same problem the other one had. Okay, so this is now data bit 2. Let me turn this on. There it is. We got a 0. Perfect. Now I'm probing data bit 3, and we turn this on. This should be a 1. And it's a 1. And then, yeah, okay. So for completeness, I will go through the rest of these. We're going to look at data bit 4 now. Should be a 0, and it is. Now we're going to look at data bit 5. This should be a 0 as well. Oh, darn it. It triggered when it shouldn't have. So I have to turn the power off again, hit the single shot, turn the computer on. Hope it doesn't trigger accidentally. There we go. Yep, it's a 0. That was, what is it, 3, 4, 5. That's 5. The next one will be 6. So we'll hit single, turn the computer on. Should be a 0. It's a 0. It's a 0. And I think the last one we looked at already, the 7, and that was absolutely a 0 as well. So this interrupt vector makes sense. This is what we should be seeing on the other board. But like I mentioned, there is without a doubt something wrong on that thing causing a bus conflict. Without a doubt, this clinches it. And what's kind of wild to me is that whatever's causing that bus conflict, you would think it would flare up and cause issues at other times. And yet the board seems to work. So something's broken on it and the thing mainly functions, and it's only a problem when the programmable interrupt controller is trying to write onto the bus for some reason. Just that one chip. And obviously swapping it with the other chip doesn't really fix the situation. So now I need to go back to the other motherboard so we can troubleshoot and figure out exactly which chip on there has gone bad. And I'm narrowing it down to thinking that it's going to be one of these bus transceivers. All right, let's think about what's going on here. So I happen to know this bus transceiver because when I took it out, that ended up turning the memory off. So that's definitely the memory one, and it's connected to all the data lines on the RAM. And then it is commoned up with the regular D bus, the data bus, not the XD bus, which is this stuff. And this was the chip, or was it, yeah, it was this one here. That is the X bus. Now, that's not an X of shame. That's just telling me that it's the X data bus. And I can double check this, of course, by looking again for where we have continuity. So there's the RAM continuity. And then the continuity on the data bus should go from this pin to this pin. They are. And then this is data line 0. We already went over this, but just to double check, goes to the ROMs there. Okay. So these two chips are what connects the data bus for the RAM to the data bus for these peripherals. And to me, it without a doubt feels like these two buses are connected together all the time. And just to illustrate that they're not physically connected, this is data line 0 on the XD bus, and this is data line 0 on the RAM. and they're not physically connected. They only go through these chips right here. And there's the connection from the ROM to that. So that's interesting because we're talking about two separate things here that are somehow getting connected together when they shouldn't be. But why is that? This has got to be a logic problem driving these chips. I'm not necessarily sure these two chips are broken. And here's why. Let me just draw a little picture showing you how these things are connected, just in case you weren't getting it off of me looking at the schematics. So the CPU, which we're going to call the AD bus, that connects to the main data bus, we'll call just D. The XD bus, where the ROMs and these peripheral chips are connected through another LS245 to that same data bus, and so is the RAM. It's through a 245. And then the ISA bus hangs off that data bus. What's confusing to me is somehow the RAM signaling is getting connected up to the data bus, and it's causing that bus conflict, which implies, because we know that this has to go through that 245, down through this 245, and to that, which implies somehow these two chips are kind of being turned on in a way where the RAM data bus output from these RAM chips makes their way to this stuff over here. But that doesn't make sense, because when we're trying to read from the ROMs or talk to this controller chip, the interrupt controller, obviously this needs to make its way to the CPU. And that means that this chip needs to be configured to take the signals from here and put them on the data bus. And then that 245 also needs to be configured to put the signals from the data bus here up to the CPU. So like to illustrate, like the other thing has to go through that, up to here. So where I'm confused is if this is configured for sending those signals from the XD bus to the CPU, how is the RAM getting back to this? Now, this chip we've already swapped out. I already swapped this, and I know that one's good because I put a different one into the socket, because that is a socketed chip right here. We know that's good. This chip, on the other hand, I haven't taken out of the board because it's still in there. Now, if this chip were somehow shorted out where there was just continuity through it all the time somehow, I don't see how the system could even work. But even if that's the case, and this was kind of bringing any signals over here into this bus and vice versa, I don't see how the RAM stuff would make its way into this bus, because theoretically, when this bus is trying to talk, back to the CPU, like here, it's going this direction, and the 245 over here for the RAM should not be turned on at the same time. This should not be trying to talk to the CPU while this thing is also trying to talk to the CPU. So I feel like there's something going on with the actual logic that controls these chips, that somehow they're misconfigured or something weird's happening. I don't quite know what's going on there. Now, as I mentioned, there are two signals that go to these chips. There's one that turns it on and off, and there's another one that controls the direction. And unfortunately, when we look at the schematics for the IBM PCXT, the XD one here doesn't show what that even connects to. I don't even know what drives that. I didn't look at the RAM one, but we can probably take a look at that to see what drives that. Because something needs to turn this off and on, and another signal needs to control the direction. But essentially, while this one is in the direction that's facing towards the data bus, like say to talk to the CPU, then almost certainly the RAM one should probably be configured that way, so that anything that's on this data bus would be potentially written to the RAM. But it really feels like what's happening is, while this stuff on this bus is trying to write to the CPU, these are getting all reversed. I hope I'm explaining that properly, but it's kind of the best of my understanding of what exactly is going wrong here. I mean, to make matters more complicated is, even though we know there's something screwed up in this logic, yet the computer still works, except for the interrupts, like everything else just works. That makes no sense. How could the computer work when there's clearly something wrong in this whole section? Now, I'm wondering if potentially there's a fixed version of the schematics that does not have this flaw, this critical error of the one section I need. Yeah, for this G pin, it's just not there. I just noticed something. Int A is right here. So it actually goes into a gate. And what does that do? That seems to have something to do with the direction signal on this LS245. Unfortunately, this logic is a little bit complicated, and this is where, my knowledge base of understanding how TTL logic falls down a little bit. I just realized something. Maybe I just need to look at the other motherboard and look at the enable and the direction signal on that board to see if it's toggling. All right, since I immediately forgot what these look like, I took screenshots of all the signals. So I'm back on the working motherboard, and I have the original, or whatever, the BIOS we've been testing with on this board. And the first signal we're going to be looking at is the MD direction pin. And I guess that's, yeah, pretty much the same. Okay. Okay, now we're on pin 19, MD enable. And okay, yeah, pretty much looks the same. Look at the top here. You can see the pattern. Okay, so memory stuff is all the same. Now I'm on the XD pin, the XD enable. And yeah, okay, that looks the same as well. Cool. And then the last one is XD direction. And looking at the top here, that looks the same. Okay, it all looks the same. Now, what I don't know is if logically this is correct. I mean, the visual waveform looks correct, but very clearly on this motherboard, the bad one, there's got to be a problem around these chips. There's just got to be. And I know it's not the MD chip because I already swapped that one out. So the only other one I'm thinking could be problematic is this chip right here, the XD chip that's soldered on the board. What if this chip has failed somehow where even though the direction and enable signals going into it look fine, what if it's somehow always connecting the bus together or something like that? I don't know. I just don't. I feel like I'm grasping at straws here with the guess that it's this chip because I just don't know. I really don't. I feel like it's got to be either the logic that controls these LS245s, because there are 3 of them, right? One for the CPU, one for the XD bus, and one for the RAM. So it's either the logic, even though it looks fine on the oscilloscope, or one of these chips, one of the ones that's soldered on the board, is somehow, you know, connecting both sides together, or it ignores the direction signal, or something weird is going on with it. It just feels like that's got to be the problem. It really does. Okay, well, I think at this point, I'm sort of stuck, so I don't really know where to go from here. So I think I'm going to socket this LS245, the one that handles the XD bus. All right, so this is kind of funny. Took it out of the board and there's like a bunch of dirt underneath it. I guess this board was really dirty at some point and I never really cleaned it properly. And well, yeah, that's pretty hilarious. So there's the new socket. There's the chip I removed from the board. Still in good shape if I need to put it back in. Here is a replacement chip. So I'm going to put this in. This is the one I tested in the memory socket earlier. At this point, the motherboard is in stock configuration, except for the fact that I have swapped out that LS245. So now let's see if that made any difference at all. I'm not confident, but my fingers are crossed. So here we go. We're ready. 3, 2, 1. No, that made no difference. Oh dear, oh dear. We're still getting the bus conflict. Still getting the bus conflict. Yeah, I wasn't really feeling confident that this would have fixed the problem because, I don't know, those chips are pretty reliable, especially the Hitachi branded ones. They don't generally have a problem. Let me just think about this for a second. Remember we saw that the int A signal on the schematic from the 8288 makes its way over to the programmable interrupt controller, but it also goes to whatever logic is controlling the direction pin on these. Maybe I need to kind of trace that and figure out which chip that's actually going to on the board here. And, you know, maybe that chip is somehow the problem. This board, by the way, has had exposure to battery corrosion. That's why a couple of these things are in sockets. You'll notice these traces actually look not in the best of shape. So we could be dealing actually with a battery corrosion issue on this board that reared up its ugly head after years. I think I've cleaned this thing up and fixed it a long time ago, years ago. But maybe something has happened. And yeah, there was like a clock card sitting in this ISA slot and it leaked right in this area. Int A signal makes its way to an LS00. And part of the problem is it's with these small logic chips that, you know, they've changed things around quite a bit on this motherboard. So it's much harder to find this stuff. So I think I might resort to using this brush. And right now it's plugged into the bench scope here. And see, we have continuity. And what I need to do is clip this onto the int A signal, which is right there. And what I can do is if I take this brush, for instance, and I poke it over here, so we have continuity, right? Because I'm touching the pin, the int A pin that's on there. So now I just need to start going around on these logic chips, seeing if I find, you know, anything on here has continuity to it. I don't need to do it on these. It's not going to be on those. It's going to be on one of these smaller guys here. Okay, there's one right there. This is a 7420. So I'm just going to put a dot on it so I know to go back and figure out exactly which pin it is on there. All right, appears to be that pin right there. So now I need to go look at the data sheet for the 7420N and see what this is doing and see, well, this is going to go into maybe some more logic chips, like some of this stuff over here, before it makes its way to the direction pin on those two chips. Okay, I'm going to use a different color marker. So I looked up this chip, and this is a quad input gate. So basically pins 1, 2, 4, and 5 all go into the gate. Pin 3 is not used, and then the output of the gate is pin 6, which is that pin there. I put a silver mark on it. And now I have to just repeat this exercise, just try to figure out, well, where this goes. And I need to trace it all the way to the direction pin on, I think it's the X chip, or maybe it's the M chip. I can't remember which one it is. I think it's the X chip. Okay, it looks like it goes over here. Not sure if it's this resistor. Nope. It's this 74LS, looks like a 27. Yep, there we go. There it is. So that's why it helps to have 2 meters. This is where it's kind of unfortunate that these clone manufacturers did try to optimize the design, IBM's design a little bit. So that's why they've sort of switched around the types of chips that are used. I mean, the logic is very similar, but then they've tried to reduce the number of chips that are in use, you know, to save every extra little penny, right? Now, the signal that's coming from here to there, the LS27 is a triple 3-input NOR gate, and pin 11, the output of that, and I'm going to mark it with this marker, is pin 8. Which is that pin right there. So I'm going to keep going down the path here. We'll move this little clippy thing over to pin 8. And oops, make sure it is not going to fall off, because it did just fall off. Now let's just double check we have continuity to the meter. We do. Now I need to see if this is going to the direction pin on these chips. Yes, it is. So this goes to the direction pin on the LS245 for the X bus right there. So to reiterate what happens, the signal comes out of this chip. This is the int A signal. It goes into this chip, comes out of that chip, it goes into that chip on that pin, comes out of that pin, makes its way to the direction pin. So these two logic chips, along with some other stuff that feed into them, are involved with the direction signal for this particular chip. And I'm wondering if it's somehow inverted or messed up. But the thing is, I also feel that's not just the direction pin. I think it might be the enable pin that's also screwed up. And I already talked about this, that we can't find what generates the enable signal for this. I mean, I can probably figure it out by just probing around on the board, going backwards from the enable pin, but the schematics from IBM don't freaking show it, which is absolutely ridiculous. So I think I'm going to quickly do that. I'm going to go backwards, and I showed you the process of doing one of them. I'm going to do the next one off camera. This is one of the reasons why having schematics is so important, because it's such a waste of time going backwards through this to try to figure out the logic when it could just been documented, and, well, we wouldn't have had to go backwards like this and spend a bunch of time, waste a bunch of time doing this. Okay, I was probing around on the motherboard, and I was really not having any good luck finding that signal. I mean, I found it some places, but it didn't quite make sense. So I decided to go back to the schematics, and I thought, you know what? The 5150 and the 5160 are very similar. So let me go look at the 5150 schematics. What we're looking at right here is the XT schematics from the 5160. And by the way, I looked at a couple different scans. They all look the same. So this is the signal we're looking for, right? It's the 244IG, and it's the LS244 1G and 2G signal, and also the enable signal, the G signal, pin 19 for the 245. And you can see there, it doesn't connect to anything. Well, let's go over to the schematics for the IBM 5150. Very similar design, it's hard to read scan, but there are the two input or enable signals for the 244. There's the enable signal for the 245, and there is where it connects to. ANBRD, address enable board. That junction, it's just missing from the 5160 schematics. It should be right there. A enable board. So on this 245 on pin 17, believe it or not, it is actually on that chip. That signal is on there. So that must be this chip right here, which I guess just carries through or boosts the address enable BRD signal. So this goes off to, well, the address enable signal that goes to, I don't know, page 10, which I think is the ISA slots actually. So it buffers it for the ISA. Now, I really don't think anything is wrong with that particular signal, actually, the address enable signal, because the ISA is working. And I think a lot of things would be completely broken if it weren't for that. And I'm pretty sure that signal is correctly turning on the LS245 and the LS244 that has to do with the XD bus. So that kind of leads me to believe that our problem has to live on this direction side of the LS245, that it's being told to go the wrong way. Now, the 5160 schematic does have this int A signal here, and the direction signal is controlled by the logic down there. But if we go to the 5150 stuff, it is not exactly the same. So there's the LS245 that's generating the XD bus, and it is going through these LSO2s. That does not match what's on this motherboard. It does not match this either. So it's not like they just cloned the 5150 and parts of the 5160. That is not the case. But either way, we look through what feeds into this. So XA9 goes into it, along with these couple signals on the LS245. So the IO read, and which one is this one here? This is the memory read and the ROM address select. So it actually looks like this has nothing to do with the interrupt controller at all. But that kind of leads me to believe that perhaps the XD bus on the 5160 is not connected to the interrupt controller. I can see that the ROMs are there, and it looks like the 8237 is on the XD bus as well. But take a look at this. There's the 8259, and it is connected on the 5150 directly to the CPU bus. How interesting is that? I was just trying to see what generates the address enable board signal. Where's that coming from? I thought it was coming from the CPU itself. Okay, here's that signal. It's generated by an LS175, at least on the 5150. And that's obviously connected to a whole bunch of different logic, like all this stuff here. Some of the signals that come from the CPU and DMA related stuff. And if we look at the 5160, there's address enable board. It also comes from an LS175. It's also connected to a whole bunch of logic. That would be very hard for me to comprehend and understand. I know people who are experts at this stuff can look at this and be like, oh, I can tell exactly what that's doing. Me, not so much. I'm not that good at just understanding all of these symbols and, oh, that's low, that should be high. This all goes through here. That's a flip-flop, stuff like that. Either way, address enable board, that goes to pages 1 and 5. Page 1 specifically, that comes in, and that's going to be going to the 8288. This is on the XT, so same. And then the other place it goes to is onto sheet 5 here. It goes into this LS244, which obviously is driving the ISA bus, and it is the enable signals for the LS244 and the 245 that connect or create the XD bus. Now, as I said, I'm extremely confident that if something was wrong with the address enable board signal, there's no way the system would work at all. Not at all. It would not be functional. So that implies to me that I need to be focusing on the direction signal that's going through this logic, and it doesn't match what's on this motherboard, unfortunately. So I'm just going to have to kind of reverse engineer it, unfortunately. But I'm extremely suspicious of this IC that happens to be right in the path where all the corrosion and damage was. The pins on there look really, really not so great. And the other chip that's involved in the direction signal is this one up here, which is further away, so I don't necessarily think that that's necessarily a problem. So even though I figured out how the int A signal goes all the way to the direction signal, let me just tone this out again, just to make sure. Okay, so that's the input of the int A signal, and then the output of that is this pin right there that I've marked in silver. So I need to probe the silver pin just to make sure that, well, I need to probe both those pins to make sure the int A signal is seen on both of those. Well, I don't know for sure if it's going to be seen all the time, but it should be seen on there, I would imagine. I suppose I could break out the other motherboard to compare, but I'm assuming I'm going to see the int A signal on both of the in and out. And that made its way over there to this, just making sure, yes. And then the output of this gate is what goes to the direction pin right there. Okay, so first I'm going to start with the direction pin on the LS245. Okay, we have activity. Let's make sure it's there consistently. Yes, it is. Now, from my recollection, that is coming out of this chip over here. Yep, same signal. Now, the int A signal comes from this chip over to there through this pin I'm on. And literally, there is nothing to see on that signal. It is just low all the time. Okay. Now, over here, I think this pin should be the input of the int A signal, the interrupt acknowledge. Didn't see it there, but it's such a quick pulse. Let's switch to normal mode, and it should capture it. There it is. There's a double pulse. Now, if I go to the output of that gate, I can't remember if it's an AND or an OR gate. I'm going to have to look at it. Okay, there's nothing coming out of it, but we need to check logically what should be happening with that chip, which is an 7420. So here's the truth table for the 74LS20. I'm pretty positive that the output of this chip that I'm looking at, which is, let's see what pin it is, pin 6, that was the output of the LS20. So pin 5 is the input. That's the int A signal. And if we look at pin 5, if I reboot the system, so that's high all the time, and it basically goes low. Now, according to the truth table, if the input to this chip is all high all the time, then the output will be low. But if any of the outputs go low at any time, in any combination, then it'll go high, the output. Now, right now, the output of this chip is just low. And our inputs that we care about are pins 1, 2, 4, and 5. So we look at pin 1, that's high. Pin 2, that's high. Pin 4, that's high. And pin 5 is high. And pin 5, we know, is the int A signal coming from the 8288. So if I power cycle the computer, there are those pulses, it goes low. Therefore, the output of this chip, which currently, if I switch this back to auto, is just low. If we set this to normal, it should pulse and go high. And it doesn't. It doesn't freaking go high. You're kidding me. So we turn on the system. It doesn't do anything. Even though, without a doubt, the input to this chip that's on this pin right here, this is a pin 5 again, turn it on, there it is going low. In fact, why don't I just hook up both probes at the same time so you can see this in action malfunctioning. Yellow trace is the output, that's pin 6, and I am currently on pin 5, which is the input, that's the int A signal. Let's switch this to normal mode, and I'm going to power cycle the computer, and my prediction is we're going to see the red trace drop down to low, and at that point, we know that the yellow trace should go up to 5 volts, and it doesn't. It doesn't freaking go to 5 volts. And just to double check, right here, if any of the inputs go low at any time, the output should freaking go high, and it doesn't. So there are two possibilities with this chip. One of them is that its output is stuck at ground for some reason. Maybe this chip over here, which I know the output of this goes to that, maybe that chip is bad. So let me double check that we're not shorted to ground, because that is possible actually. We are not shorted to ground on that pin. It is not shorted to ground. It's not shorted to 5 volts. So yeah, and it should be going over here, I think. Yeah, it goes there. So that chip has got to be bad. Either this chip is bad or that chip is bad. Like maybe when this chip gets turned on, this SGS chip, it's a 74LS27, maybe it's somehow holding the input down at ground, but it's certainly not at ground with the system turned off like this. My prediction, because this one was in the path of the battery damage and the corrosion, that chip has failed now. Socket is installed. This is the chip that I've removed from the board. I guess I don't have one of these handy, but I do have the other motherboard, which has exactly the same chips on it. So we can just steal this one right out of there, 74LS20. And what I'm going to do before we even hook up a CGA card and power this computer up, we're going to take a look at that exact same signal we just looked at before that seemed broken, and we'll see if it looks better now. So here we go. Are we ready to see if this is fixed? And I guess if it is, we're going to see multiple hits of the interrupt 0 every 18 milliseconds, because the BIOS should not freeze. Even though I don't have the CGA card in there, I think it should still get further than it was getting. So here we go, 3, 2, 1. Yes, yes, it's freaking working. It's fixed. You can see how it's changing, it's shimmering. That is because the interrupt 0 is firing multiple times, and we can see exactly the way the signal should look, but this freaking chip is bad, the one I took out of there, because the yellow trace never went high, and therefore the direction signal, which was coming over here from this chip, which is the LS27 that goes to the direction for this LS245. So the direction signal was not getting turned off at the right time when it should be. And now it is. And that fixed the motherboard. That freaking fixed the motherboard. So let's get a video card installed in this thing, and let's see this computer actually freaking boot. Here we go, CGA card is in. Let's turn this on. There it is, it's posting. And I think it should go to basic as well. The keyboard's not connected. It might be trying to load the floppy. Oh yeah, there we go, basic. Okay. Yeah, I don't have the floppy controller hooked up, so that's why it's running so slowly. This machine is freaking fixed. Yes! That feels super gratifying to have been able to find this bad logic chip. This little chip, it was keeping the computer from working in such a subtle and unusual way. So I am going to spend a moment to clean up all of the mess I've made with like the paint markers all over this thing. Let's get this cleaned up and looking the way it looked before I started this endeavor. Unfortunately, I can't fix the fact that I socketed an extra chip that I shouldn't have, but at least, you know, there was no damage to the board. I mean, look at these traces here. That does not look great, does it? Okay, everything is cleaned up. No more marks on anything. GlaBIOS, the stock version is loaded onto here, not my kind of hacked up copy, just because I wanted to run all the diagnostics to make sure this thing is working. CGA card, floppy drive controller, it is hooked up to a floppy drive. Here's the bad chip that doesn't have the X of shame on it yet. And I went ahead and hooked up an actual speaker, along with a keyboard. Let's see what happens when we turn this thing on. Yes, it is booting. That is awesome. And let's see what this does. Floppy drive is going. And it's loading Alley Cat. Uh-oh. I think we have a fault still because there's no music. That's a problem, isn't it? So let's reboot the computer here. Uh-oh. Okay, long, and 5 shorts. Pick test register failed? Are you kidding me? Programmable interrupt controller? So long, and 5 shorts. Yeah, let's turn this thing back on. Yep, that is definitely that test. So this thing is fixed, but not quite fixed. Okay, well, let's get these cards out of here. So the pick test is testing the programmable interrupt controller, and it's seemingly unhappy for some reason. Let's just make sure I didn't bend any pins when I pop this in. Wow, this really loosened the socket, actually. These sockets can be kind of crap because look at this. I could just like lift this out with my hand. It's that bad. So we could have a problem with the socket itself, but we also could have a problem with this chip because this is the one I socketed, right? And this has to do with that chip. But the thing is, without this in there, it's not going to be able to run any code. So if I turn this on, we get nothing. So this does need to be in there for any kind of code to run. Doesn't make me feel confident about this computer's reliability. Yep, there's the failure. And let's hit the reset button on here. So that time it posted. That time it posted. That time it errored out. So I'm going to push down on this chip, and it's posting now. Let's see if we get errors. Yeah, okay. I bet you it's just the socket is damaged now or something like that. It's my hunch if I take the programmable interrupt controller out altogether, then we'll just get that beeping immediately. Yes, we are. And yes, I know if I had a double wipe socket in here, this socket would not be having a problem, especially with this chip, which doesn't even have cut legs. These legs are normal, but it is extremely worn out now. I think because I was putting stuff in and out of it so much. Okay, what I'm gonna do actually, we'll just pop this out here. I'll just use my hands to do it. There we go. And I'll put some deoxit in there. I mean, this chip is, you know, a little bit oxidized. So we'll get a little deoxit in there. And who knows, maybe that'll just help it make a slightly better contact. Okay, everything seems to be working pretty reliably. I'm just gonna bend the board a little bit, see if that causes it to fail again. Tap on the board. No, okay. Good, seems to be working now. The floppy controller's back in. I also flashed the fast version of GlaBIOS back onto the 1ROM, and let's see what happens. Oh yeah, oh, I guess I have a little bit of a problem with the keyboard there not working, but it started booting so quickly, and the music works, which is good, because it froze last time. Does the keyboard work? Yes, the keyboard actually works, but I think I deleted some part of the keyboard test routine that results in an error. So are we a kitten? Yes, we are. And there we go, the game is working. Oops. Oh no, get away from the dog. I'm really not good at this game. There's tomcats and I'm a little kitten. Oh no. Does that bring back memories for anyone? Let's just see again how quick that boot process is. Power off, and I'm gonna power this thing on. 3, 2, 1. There it goes. The disk drive is loading that quickly. I love this modified BIOS. I love it. Obviously, it doesn't run the diagnostics, and that can result in, of course, freezing because, you know, that PIC chip wasn't in the socket very well. But everyone knows what time it is. It is time for the X of shame on this chip, which caused me to make 2 videos trying to fix this motherboard with this faulty IC. So that is going to be it for this repair. If anyone is still watching, thank you very much for sticking with me. That was quite challenging just to kind of get to the bottom of exactly what was wrong with this chip. Once I figured out I was seeing a bus conflict with the interrupt routine happening, and I could see it, that kind of got me on the right track. Now, the funny thing is, if I just sort of gone over all of the schematics first, I would have seen that that int A signal didn't just go from the 8288 to the PIC, that it actually went to some of the chip-select logic that controlled the LS245s. And if I had done that, then maybe I could have shortcut some of the process of figuring out, you know, what was wrong, because it was apparent that everything worked perfectly on this motherboard except for hardware interrupts. And honestly, it's that int A signal that is part of that whole hardware interrupt process. And of course, it makes sense that the logic that sets up the LS245 direction and whatnot, you know, if that was having a problem because the input from the int A signal wasn't getting through to it, it would be, you know, sending the signals the wrong direction at the wrong time, and it would be creating a bus conflict, which is exactly what was happening. But this process for me is a learning experience, and I haven't done that much repairs to PC motherboards, so I'm very unfamiliar with PC architecture when it comes to how the whole interrupt handling routine works. This was honestly the first time I've ever really looked into it, and it was a great learning experience. So hopefully the knowledge sticks in my mind, so if I ever have a problem like this again, I'll know how to kind of shortcut the process to try to figure out what's wrong without having to go down like so many different paths and whatnot and create these 2 very lengthy videos. So anyhow, if you're still watching, thanks very much. Thumbs up if you liked it, thumbs down if you didn't like it. Comment down below on your thoughts about my process and whatnot. And please, I'm always open for tips and tricks and stuff. If you have experience fixing these types of logic problems, let me know what I kind of messed up. I know I made some rookie mistakes here and amateur hour stuff, but it's all part of the learning process. And look, I'm no expert in fixing PCs, and I'm not expert in the 8086 architecture. So every time I work on a board like this, it just gets me a little bit more familiar with how this whole thing works, and that's great. I love the knowledge. So that's going to be it. Stay healthy, stay safe, and I will see you next time. Bye-bye. Look at this guy. Ugh, bad chip.